Gauss's law. Gauss was one of the biggest mathematicians in the story. He was compared to Aristotle, and we will learn about Gauss. For example, FFT analysis was mathematically prepared by Gauss 100 years before it was applied in electronics. And we discuss Gauss' law, one of the lot of laws that he established in the field for electric field. First, we should start with flux, with flux and flux of the vector. Let's have the line, for example, this is a line of vector E electric field, but here you can have any vector field, and if we put here perpendicularly to this line surface S, we can make calculation of the flux of vector E through surface S, and letter phi will be applied for flux from formula E multiplied by S. This is the simplest way to calculate the flux. If we change the position of the surface, for example, we will have the angle between surface and here is the vector perpendicular to the surface, and here is the direction of flux. Here we have angle alpha. In this case is equal as cosine alpha is proportional to E multiplied by S and cosinus alpha. We see that in this case, when we rotate the plate, the flux became lower because of cosine alpha. This we can write in such a way: E dot product of E multiplied by S, where S is a vector of surface vector, and we define such vector in such a way. This is vector S that is perpendicular to the surface. And have the value of surface multiplied by versor unit vector perpendicular to the surface. And we have, of course, two such vectors to not create problems. We always make the direction of the ball of the lateral line of this surface, and we take into account only this vector that is connected with the direction of this movement according to the right screw rule. So if you have right hand screw that goes in this way, this is the direction of surface vector S. And this is a case, this formula we can apply only when E is constant and when angle between E and S is constant. Only in this case we can apply this simple formula. For the case when our surface is, for example, like this, and electric field line of electric field are like that. In such a case, to find the flux through this surface, we have divided the surface to small pieces of surface, differential surface. Differential element of surface, ds. We should know the value of vector E in this point where we have ds, and make the sum of all flux through this very small element. And in the limit of this sum, when ds goes to infinitely small piece, we can write flux as an integral over all surface S from E ds. And here we have dot product of two vectors. Please remember that we have here dot product of these two vectors. The same here as here we have the dot product of vector E and vector of surface. And now we can write the Gauss law for electric field. This Gauss law is valid only in vacuum. Later we will learn about Gauss law that is valid in all mediums. In vacuum, this is the flux, because this is the flux of electric field, and this circle over the integral means that this is integral over the closed surface. And now I will give you the Gauss law. The net electric flux that pass through closed surface S, the net electric, the total or net electric field that pass through this closed surface. For example, we can have such, and as well such field. We have to make some here enter, here go out, this flux go out, and sum of this all fluxes is equal to the net charge enclosed in by the surface divided by epsilon 0. So here we have all kinds of charges. For example, Q, surface charges, sigma Q, line charges with density tau, and as well you can have volume charges with density rho v. All kinds of charges that we can have inside of this closed surface have to be put here. This must be the sum, algebraic sum. Here we have algebraic sum. So, one more time. The net electric flux that pass through closed surface S is equal to algebraic sum of all kinds of charges that we find inside of this closed surface or enclosed by that surface divided by epsilon 0. And it doesn't matter where we can move these charges, change the position, but the flux always remains the same. And now we have to understand the Gauss law. First, if the flux is equal to 0, does that mean that we doesn't have Q, we doesn't have charges inside in this closed surface? Of course, if we doesn't have charges, it always gives us flux equal to 0. But my question is, if we have flux equal to 0, can we say that we doesn't have charges inside? We can't say this, because we can have, for example, plus Q and minus Q. And so, as you see, we have charges inside, but the algebraic sum of the charges is equal to 0. And second, if we knew that Q is equal to 0. We doesn't have charges. Can we say that E is equal to 0? No, we can say this, because we can have such situation. Our surface is in external field, and we have here electric field. It is not equal to 0, but inside Q we doesn't have any charges. So you have to understand the Gauss law. And we try to apply Gauss law. We can use the Gauss law, we can find electric field distribution. First of all, let's check the Gauss law for point charge. We have a charge Q, positive charge, and we surrounded by Gaussian surface. This closed surface, we can call it a Gaussian surface with radius r. And let's put the Q at the center to make calculation easier. And now we can write the electric line that are like this. And we can see that at every point that we check on the surface, ds, differential surface element, is parallel to electric field, the vector of electric field. And now we will make this calculus. We make this over the closed surface S, E, ds. And we can write that E is parallel to ds over all surface. In each point of the surface we have such case. So our integrals we can write in this way. Multiply by cosine alpha, but alpha is equal to 0, so cosine alpha is equal to 1. So this is all. That means that we can take module of vector E and module of vector ds. This is the module of vector E. This is the value of E at the distance of R. But here we calculating through the surface that radius is equal to R, big R. We see that this is constant, so we can put constant before the integral, and here we have ds. This is unit integral. In unit integral, unit surface integral, the result is the surface. And I believe that you know the value of the surface of the sphere, so I at once write the result. And here I will write 4p r squared. And now please see, this with this we can cancel. 4p with 4p, here is q, here is q, and we have q divided by epsilon 0. So we see that Gauss law is working here. It's okay. The same result we will obtain if we change the position of q. Any position of q give us the same result. But the calculation for such cases are much more difficult. For this it is easy because I was able to calculate it in very fast way. This is constant. We can put this constant even here before, because we can write here that on the surface with radius r, E is constant. So even here we can put it before. But we can see as well that when I wrote the value of E, everything is constant here, so the calculation became very easy. During the exercise, we analyze symmetrical cases in which on the surface E is constant, and using this using Gauss law, we will find electric field intensity. And now mathematical supplement. This was the integral form of Gauss law. We learn about differential point form of this law, but before I make it, I will present you mathematical supplement. Divergence. Divergence definition. Definition of divergence. This is the and design sketch that explain this. We make, this is the closed surface S. We calculate here is the V. We calculate flux of the vector E through this closed surface and divide by the volume of this small piece. This is definition, and we never use this definition for calculus of to calculate divergence. We calculate the divergence from another formula. For Cartesian coordinate system, divergence E is equal we see that the result of divergence is the scalar. For example, let's vector function have such two such vectorial function, and we want to calculate divergence. So we have from the first one 4x, pu 3x, and pu 4x. So we have 11x. This is, of course, number. This is variable, but it is a real number as a result. When we choose for every point in the space, we can find the value of divergence, and this is the number, scalar. And you should remember this, that for another coordinate system, divergence is calculated in another way. This we can write divergence of E, we can write as well as Nabl operator multiplied by, and this is dot product. This is dot product of the Nabl operator by E. We can write divergence in this way or in this way. For another coordinate systems, divergence is calculated from different formula. I will give you the in meantime I wrote divergence in cylindrical coordinate system, this one, and for spherical coordinate system, and we see that it looks like this. We should remember only this calculus, this formula. This is the calculation of divergence in Cartesian coordinate system. And to make summary, result of divergence is a scalar or scalar function. So it is number or scalar function. And now next, gradient. Gradient is an operator that from one electric field, no, from scalar field create vector field. So using the gradient, apply the gradient to scalar field, we obtain vector field. Let's write the definition of gradient. I use letter E, electric field intensity, but no, here should be phi. Here should be phi. That is this is any scalar function. And we'll give you an example. We have function and now we want to calculate gradient. This is the vector function, and 8xz pu, when we second give us 0 and the last one give us 4x az. This is versors, and here we have component x and component z. So from scalar function we obtain vector function. The same from scalar field we obtain vector field. Applying operator of gradient, we obtain from scalar field vector field. And gradient can be written in the way but we should remember that here is the scalar function. Here we should scalar function and nabla operator. I will write it one more time. This is a vector and as before, gradient, when we this is the calculation of gradient in Cartesian coordinate system. And this you should remember. For another coordinate system, calculation of gradient are different, and I will write it for cylindrical coordinate system. Gradient phi is equal phi pod rho and versor of rho, and second 1 divided by rho d phi pod alpha e alpha, and d phi pod z e z. This is easy to remember, but much more complicated is the gradient calculated for in spherical coordinate system. But maybe I will try it. I will write it so you have. This is cylindrical. This is spherical. We can calculate it from d phi pod r q and this is in spherical coordinate system. And now relationship between potential and electric field intensity. Electric field versus potential. I make a sketch. In the center we have charge Q, positive charge. We see electric lines that goes away, and I wrote equipotential surface. Potential is growing in this direction, so phi1 is bigger than phi2. And now I take two equipotential surface very close one to another. L is going to 0, very close one to another. And I will write the energy changes when we move charge Q. We move charge Q0 from surface with equipotential value phi q delta phi to this equipotential surface. The energy changes, the changes of potential energy is equal final position, this is the direction, minus start position. phi minus delta phi, q delta phi, q0, q0. So we obtain minus q0 delta phi. So we see that energy go down. In the same time, this energy changes is equal to the work done by electric field, because moving charge q from position 1 to position 2, electric field make work of electric field that is equal F dl. In our case, L is going to 0, so dl we can write here dl differential distance, so we can write that work done by electric field is equal F dl. This is Coulomb's force, and because the work is, if we leave free this charge, it moves along the electric lines. So F is parallel to the L, so we can write here without vector. And finally, we can write Coulomb's force as a Coulomb's force as a Q0 multiplied by E dl. And we can make comparison, because electric work done by electric field is equal to the potential energy changes. So Q0E dl is equal to minus Q0 delta E. So we can find that E is equal minus delta phi O dl. This is the calculation, differential. This is the differential calculation according to the coordinates. So we can write this like a gradient. This is minus gradient phi. Gradient phi. So finally we can write that vector of electric field intensity is equal minus gradient phi. This is very important. Formula, because if we know distribution of potential, we at once, making this calculation, we can calculate electric field. And let's one example. During the exercise we had such case. Here was the charge on the circle of radius r, and we have to calculate E in this function of E over the axis z. It is very easy to calculate potential in this point. Potential function in point 0, 0, z is equal to tau 2 epsilon 0 multiplied by r 1 divided by r squared 2z squared, and let's go root square from this. And now to find electric field, we have to make gradient. We are fortunate because we calculating this gradient. If we make derivative for x and y axis, we obtain 0 because we doesn't have the variable that correspond to this axis. The only derivative that we should calculate is according to z. So let's make r2 epsilon 0 1 by r squared 2z squared and roots of this, and we make derivative according to variable z. So we see that we have, this is t, this under we call t, it is the minus, so it is minus 1, 2, t2 minus 3 by 2, and internal 2z. From z square, derivative is 2z. So we put everything to this formula, and we have that E is equal to minus gradient phi, that means minus that what we obtain. Minus give us q, tau r z, 2z minus, and this is cancel, 2 epsilon 0, and here we have r squared z to the power of. And as you can see, this is this function. This is vector function that give us the value of electric field intensity over the axis z. And this is the way of calculation. Numerically, if we calculate numerically, firstly we find potential distribution in the field, and when we knew potential distribution function that describe potential distribution, we can, using the gradient, we can calculate the electric field intensity. This is the simplest way to finding the electric field intensity. Gauss, Ostrogradski, Green equation. We have renamed. There were scientists that introduced this equation quite in the same time, so we have renamed. But in Germany it is called Gauss, in Russia Ostrogradski, and Green for English-speaking people. This is law, equation, that govern any vector field. This is the flux through closed surface S, and it is equal to volume integral through divergence E dV. This law, this equation, is valid for any vectorial vector field. We apply this to obtain point form of Gauss law. I write one more time Gauss law. This is Gauss law, and on right side I will write charge as for volume charge, volume distribution of the charge, integral rho v dv divided by epsilon 0. And now we can apply to left side of this Gauss law, integral form of Gauss law. We can apply our Gauss-Ostrogradsky green equation. So we have on the left side v divergence A dv, that is equal rho v divided by epsilon 0 dv. And now when two integrals are equal, they are equal because the limits are the same. They are equal when this is equal to this. So divergence A is equal to rho v divided by epsilon 0. This is point form of Gauss law. We can write it in such a way. Both are correct. We can use this or this formula. They are the same. Point form of Gauss law, point form of Maxwell law will be much more useful than integral form, and we learn it during the next lectures. And now we see that we have two formula that I write one more time. First, this one. Divergence of electric field intensity is equal rho v by epsilon 0. And we know that gradient is equal to the gradient of potential phi is equal I write it like this. Minus gradient phi is equal to E, so we can write it like this. Okay. Minus gradient phi is equal to electric field intensity. We can put this in this place. So we have I put this in this place. This is two-time Nabel operator multiplied by Nabel operator. we call this as it gives us scalar operator that is called Laplacian. And we write it like this: delta t is minus rho v divided by epsilon z. And this equation is called Poisson equation. Special case when charge in the place where we doesn't have charge. This is for the place where we have charge, volume charge distribution. In the part of it where we doesn't have charge, of course, right side is equal to 0. And this is called Laplace equation. This operator, how it looks like. For example, example. Let's have potential. This is any scalar function. It do not have to be potential. It's any scalar function. For example, 2x fair z. Such function. And now we calculate so this is second derivative from phi according to x-axis. So we have 3 and after 3 multiplied by 2 give us 6 and multiplied by 2 give us 12x y squared z. Pure. First derivative from y squared is 2y, and second one is 2. This is 4z, a pure 0. First derivative will be this, and second will be 0. So this is the result of when we apply a Laplacian operator, Laplace operator. Laplace operator. And now, what is how to solve this equation? This is second order differential equation, and the solution of this equation is given by integral. So solution of the second order differential equation is a potential, the point x, y, z, reference point is in infinity, and the potential in reference points is equal to 0. So if we look at the previous former, you look at the former lecture, you will find that this is the calculation of the potential for volume charge distribution. So that is calculation of the potential of volume charge distribution. How to find Laplace solution? Solution of this equation is found by numerical method. This is calculus, computer calculus, numerical computer calculus. That is this special method that can calculate, for example, we have two surfaces, one with potential phi, for example, equal 1000 volt, and second one 0 volt. Numerically we can find the potential, we can find the potential distribution, because here we doesn't have charges, so we can find potential, the distribution of potential, equipotential surface. You can find potential is growing in this direction, and here near is equal to 0. And when we have, this is for example one of the phi constant, one of the equipotential surface. When we have this distribution, there are special program, numerical program that find this distribution. After this we calculate the electric field distribution. So we can obtain electric field distribution. In this way, for example, when we have laser that is excited by electric field, we can obtain optimum electric field distribution, that when we have breakdown, we excite the plasma that we have here in a uniform way. This is to obtain impulse laser of high power. And there is a lot of different application of this method for finding the electric field distribution in the space. Conductors in electric field. Up to now we discuss the cases where we have vacuum, charges and vacuum. Now we introduce conductors, new material that we call conductor, and definition of conductor. This is material that allows that allows the flow of charges. So charges can move in this material free, that they can move free, and additionally contains free charges. So for example, electron positively charged holes, positive or negative ions. All this we can call conductor. Conductor, what happens with conductor if we apply electric voltage to this conductor? Let's have conductor. For example, this is a conductor. So we have inside free charges, and additionally they can move easy in the volume of this conductor. And let's put this conductor in the moment of T0 in a uniform electric field. So at the moment of T0 we put it in electric field. Of course it is easier to apply. We have conductor in this place and we apply suddenly in very fast way electric field to this conductor. What's happened? We analyze positive charges. What happened with positive charges and negative charges? Positive charges move, all positive charges move in this direction and force that we have over each of him is equal to Q multiplied by electric field intensity. This is electric field. At the same moment, negative charges goes in opposite direction. And after time that we call it relaxation time, we obtain stable static situation. This is the same conductor. In a static situation. And what's happened? Static situation, or after the passing time have to pass. Time is T0 pu tau of relaxation time, constant. We obtain the situation because if we have state situation, so charges doesn't move anymore. So when they do not move anymore, when electric field, internal electric field is equal to 0. Only in this case charges doesn't move anymore. At the same time, electric field change the lines, changes its way. What's happened? We see that electric field change. It's how the path, and in every point they enter to the conductor at right angle, because if not, there will be the electric field tangential electric field that move the charge, that will move the charges. So if you have state case, only field that is perpendicular to the conductor give us a constant distribution of charges. And now here we have on the surface, very close to the surface, positive charges, and very close to the surface, negative charges. And this is stable. What is important to remember? First of all, please remember that for electrostatic field, internal value of electric field intensity is equal to 0. This is very, very important. Very important, and you have to remember this. That for electrostatic, we have internal value of, in stable condition, of course. If we have stable condition, static case, electric field is equal to 0. This phenomenon is called electrostatic induction. Electrostatic how we can call it? The appearance of charges over the surface of conductor under the external electric field is called electrostatic induction. This phenomenon is called in this way. And now I will write now, this is negative charges. Here we have negative charges. And now what interesting. We make such we left only very thin part of conductor and take away everything that we have inside here. And what happens? Nothing. The line remain the same in the same way. And what's important? We still doesn't have electric field inside this this conductor. This case in electronic is very important. Engineer very often use this kind of application of this conductor, and it is called shielding. Shielding of electrostatic shielding. Electrostatic shielding. It is used, commonly used when we want to isolate some part, some volume from electric field. We are using electrostatic isolation. We have to construct it from conductor. And this electrostatic shielding have efficiency of 100% for electrostatic field. But what happens if it is not electrostatic case? That means that electric fields change the direction. In one moment is in this direction and after in this direction. And when we move we start to move this fast and more fast. The charges flow from one side to another side. They have flow from one side to another side. So we will have currents of the electric current. This current create new electric field that can enter in the shielding area. To avoid this, special construction of this shield is made, and this special construction is called Faraday cage. And this Faraday cage at the building of C4 at the Department of Electronics, on the bottom in the basement, there are several such Faraday cage where your phone doesn't work. You can when you enter in such in such Faraday cage, you do not have any signal on your mobile phone. So nobody can call you, and you as well can't call from the from this cage. At the building of C13 there is very big cage where even tear can enter there, and in this cage our colleague from university, from Department of Electronics, carrying on research on electromagnetic compatibility. For example, they create impulse of very high energy of electric field, and they try to find how resistant this instrument is equipment to this shock, electric shock. And they measure as well, because ambient is poor, is empty for electric field. You doesn't have any electric field inside. They can measure what is the noise produced by electric equipment, and they do such research for the firm that produce electric equipment, because norm tell us what is the level of noise that is allowed for every kind of electric devices. So Faraday cage is a very useful tool for making the research of electromagnetic compatibility. And now, what will be the distribution of the charges on the surface? Because all charges goes to the surface of conductor. And let's make an experiment here to find a relationship between the shape of conductor and the electric surface density of charges on this conductor. And we make experiment. We have two balls of conductor charged with the charge in special way. Let's take one ball and second one bigger. We charge it with charge Q1 and charge Q2, and in the way that potential of Phi1 is equal to potential of Phi2. If we have ball, potential of course the charge goes on, to the surface of this ball. This is conductors with radius R1 and radius R2. And what's happened? We can calculate potential Phi1. Phi1 is equal to 4P epsilon 0 Q1 divided by epsilon by R1 to the squared. And Phi2 is equal to 1/4P epsilon 0 Q2 by R2 squared. Now these two potentials are the same, so we can cancel this, and I write, because Q is distributed like surface, because all charges go to the surface. Charges of so I write Q1 with surface charge density. Surface is 4P R1 squared, and charge density Q1, it is equal divided by squared and no, here is without, sorry, this is potential. And second one is 4P R2 squared sigma Q2 divided by R2. And we see that density of the charges are inversely proportional to the radius of these balls. And somebody can ask, what is so important, this result? Why we came to this result and what it gives us? And now, please look, if this is two potential with the same value, we can connect this and create one piece of conductor. And charge doesn't move because the potential of two balls have the same value. And now we can see that charge distribution is inversely proportional to the radius of curvature of conductor. So here will be a lot of charges, when here will be much less charges. Here we do not find charges. So here will be a lot, here will be much smaller number of the charges. And what what we can, when we can apply this knowledge that we have. It was found, for example, by Coulomb. When he made his research, when he wanted to obtain the law of Coulomb, he noticed that when he hang up the ball and charge it, this was very good isolator, the charge goes away. After some time it goes away. And it was very strange for him, where this charge go away, how it is possible. And he cleaned the ball, he polished it, and he noticed that the velocity of the going out of the charges became much smaller. Why? At this time he was not able to explain this result, this phenomenon. Today we know that when surface was not polished, they have small peaks, and a lot of charges came to this small piece and create in this point very high electric field intensity. We learn that electric field intensity near the surface, normal of this, is equal sigma q divided by 2 epsilon 0. So when the electric field density, when there is a lot of charges here, so here is big electric field intensity, and this attracts negative ions with much higher force than for uniform distribution of the charge. So here, much faster, there was the emission of the charge from the surface. Another practical aspect of this phenomenon. This is the Earth with radius of Earth. And here we have the peak. So the charges goes here to the peak. Here we have very high electric field intensity, and we have breakdown of the air and breakdown of atmosphere. This phenomenon was noticed by Benjamin Franklin, and he created a method for defending the buildings against this phenomenon. This is the invention of Benjamin Franklin. And there was another practical aspect. When we have this is the electric wire. This is the electric wire with isolator. Let's make the isolator green. And if the wire was in the high potential, for example 20 kilovolt, it may happen breakdown here because here on the curvature we will have higher electric field intensity than in another place. Here is much lower electric field intensity, here is the electric field intensity higher. Isolation is thin here, because when we bend, the isolation became thinner. So in such places we can obtain, we can have breakdown, and this is what tip we can give. Electric wire over the high potential can't be bent. It should be with very low curvature, because it is dangerous that we have here breakdown. And the last case, if we have very narrow peak of conductor in the range of nanometer. When we have so small peak of conductor, very strange effect. We can find that we see very strange effect. It is called electron tunneling, and even for very small value of electric potential, we can have emission of electron from this narrow peak. Electron go away. Even with 10 to 40 volts, we can have this emission. So in the 2000 there was new kind of display with in 2000 there was the presentation of very good with the display that was called site emitting display, and it was constructed in such a way. Here was the matrix of these peaks, very narrow, very small, and here was the luminophore. So this create the pixel on the luminophore. At this time luminophores were very good developed. The quality of colors were excellent. And this was much thinner. This display was much thinner than kinescope. Kinescope was very huge lamp to obtain here the display. It was thin, and the quality of the picture was excellent, much better than existing at this time plasma. And no, plasma was not present at this moment. It was LCD. That was the start of LCD. And this display that inventors wanted that it substitute kinescope. The life was only one. Seed display was created from the matrix of very thin 9 nanometer scale peaks. At the time the etching technology was achieved big progress, so we can obtain very narrow these peaks, and with the voltage 10 to 40 voltage we obtain the emission of electron. when the electron falls down on luminophore, we have the pixel of light. This display have very good contrast, not available for another kind of display at this time, and refreshing time smaller than 1 millisecond. And it seems that this will be the future for TV, for displaying. But at the same time, LCD make a big progress, and LCD became cheaper because still everything of this have to be in vacuum. So it was very difficult technology to obtain vacuum in such big volume. So LCD killed this technology.